Okay, in this video we'll have a look at stationary points, and stationary points are locations on a function where the slope of the curve is 0 or where the tangent slope is equal to 0. So we need to figure out what makes our derivative here equal to 0. That's the slope that we're interested in for stationary points. So let's get our derivative first and foremost. So if we differentiate this cubic polynomial, we'll have 3x squared plus 2x minus 8. And we want to find the x value or values that make our derivative equal to 0, because that's the slope of the curve we're interested in for a stationary point. So we have to figure out what makes this quadratic equal to 0. So that's a pretty familiar situation. That's our quadratic equation. I guess standard quadratic equation approach is get everything to one side and have a 0 on one side. Well, that happened kind of naturally here. So let's figure out what x values can make this expression equal to 0. And you can use the quadratic formula, but I believe this is factorable. So let's have a look. What adds to give me the middle coefficient and multiplies to give me the outer numbers of 3 times negative 8, or 24. And this is definitely factorable because 6 and negative 4 will give me that product and will give me the sum of 2. So remember those numbers in this factoring, I guess and check approach I'm about to use here. Those numbers are the x coefficients I want when I have a look at expanding out my factored form here. So we have 3x squared, and if I multiply 3x by a plus 2, that gives me 6x. Which would mean I have to put a subtract 4 here. So my inner terms can give me the minus 4x. So there's a factoring review in the midst of our calculus here. And I guess we should check, the guess and the check method. So I see a 3x squared. I'm just expanding it in my head, and I definitely see a 6x minus 4x, which gives me that plus 2x middle term. And we also have minus 4 times 2, which is negative 8. So this means there's 2x values where this derivative is equal to 0. So there's going to be 2 stationary points. So to solve those for those x values, we're using our zero product property here. Maybe scroll up a little bit. So what makes 3x minus 4 equal to 0? We'll add 4 and divide by 3. You'll get 4/3. Your first x value of your stationary point, and the next one's a bit easier, so x equals negative 2. So those are just the x values, but keep in mind we need the coordinates as mentioned in this question. So unfortunately, the annoying parts, we have to evaluate our function twice. Maybe we'll start with the negative 2, and the 4/3 isn't going to be much fun. So this very well could be a paper 2 problem, but let's see if we can suffer through it completely with using pencil and paper methods here. So this one's not bad. I evaluate this cubic polynomial at negative 2. You're going to get negative 8, negative 2 cubed, plus negative 2 squared, which is 4, and then minus 8 times negative 2, which is plus 16. So this y value is going to be 20 minus 8, or 12. So that wasn't too bad. And maybe I will just wrap up down below here, at least with that first stationary point. We have the full coordinates now. It doesn't matter what order you write these down in. So when x is negative 2, this function outputs 12. So these are the coordinates for our first stationary point. Remember where the tangent slope is 0. And then the annoying one, of course, to evaluate, the annoying x value is 4/3. So we have to put 4/3 into this cubic polynomial. So if I cube 4/3, and maybe I should write it out, it's not only a factoring review question, I guess a fraction review if you're rusty with your fraction chops here. So 4/3 cubed, 4/3 squared, and then minus 8 times 4/3. So that's going to give me 64 over 27, cubing the top and the bottom, and then squaring top and bottom, and just multiplying 8 times 4/3, which is 32 over 3. So we need to get a 27 on the bottom, so let's go with 64 over 27. This is more work than the calculus, I think. Times top by 3 and bottom by 3, that's going to be 48. Over 27, and then unfortunately we need to times the bottom by 9. So what is 32 times 9? It's going to be 270 and 18, or 288. Okay, so this is definitely more work than the calculus part of this question. So what do we got in our numerator there? We're going to have 112. I'll just do that over to the side. And then I got to subtract 288 from that. So I'm just going to do the difference between 112 and 288, and knowing that it's negative, because 288, of course, is the more negative number. So that's 176. So that means our y value, without the aid of a calculator, which was probably foolish, is negative 176 divided by 27. And if you're struggling with that, I don't think you really need to struggle with that. Just sharpen up your fraction chops and keep in mind it's probably a paper 2 question anyway. If you're worried you would have to do that much fraction work, but if you can handle calculus, I'm sure you can handle this fraction work. So the x value of 4/3 outputs this kind of horrible negative 176 all over 27. So let's actually have a quick look at our TI Inspire and just confirm those 2 points, stationary points, and also make sure you understand what a stationary point is. So we should see a flat horizontal tangent slope at those 2 sets of coordinates. And I guess we can also double check my arithmetic there at negative 176 over 27, that y value. Okay, so here we are in the TI Inspire. Let's load the graphing app and we'll have a look at what this cubic polynomial looks like. So what was it? X cubed plus x squared minus 8x. And that's what it looks like. And then let's see, can we resize that a little bit? Actually, I think I'm just going to resize the y-axis. So I'll leave that where it is and just double click on those numbers. We'll go up to about 20. And then I don't know, what do we need to see? Maybe negative 10. I guess negative 8 was good enough. I guess if we can see the bumps there, we're good to go, because those bumps, which are kind of reminiscent of a vertex, shape of a vertex and a quadratic opening down, and the shape of a vertex of a quadratic opening up, bringing back memories of a quadratic, of course, but that's actually what your stationary points often look like, these vertex-like things. Now, of course, we shouldn't be calling them vertices, because that term is reserved for quadratics, of course, because this is a cubic polynomial. So we'll just use our new terminology here. We'll say they are stationary points. So let's trace, and we'll type in those 2 x values. The first one was negative 2. And there's our first location of our turning point. And the next one, who could forget the 4/3 ordered pair? And we can see it coming up in decimals there as well. And I recognized the other day that if this label's annoying you, you can actually just slide it off the graph, and it seems to just hide it and disappear. So I like that. So I guess there's one other thing too. We can go to our calculator window and check the decimal, I guess, to make sure that, what was it, negative 176 over 27 is indeed that negative 6.5-ish point. But we can also just redefine that ordered pair that we got using the trace feature by clicking on the x value and typing in the exact x value. And once we do that, the calculator will output a fraction as well. So the way the calculator is finding those y values in the trace feature, it seems to prefer decimals, but it's not too difficult to redefine that ordered pair by clicking in once again after the point appears on your curve, clicking in the exact x value to get the exact y value. And I actually prefer this approach, so I don't have to load the calculator app and switch back and forth and try to keep a decimal representation in my brain as I'm going back and forth, and possibly lead to stupid mistakes as well. So here we got our 2 stationary points, the coordinates of both of our stationary points in their exact form on our calculator window. And maybe one last thing before we wrap up this video, let's put on our tangent lines using our geometry. First menu, points and lines, and number 7, tangent. And once we click on that point and that point, we can see that we definitely seem to have a flat horizontal tangent lines, or I guess what we should say, horizontal tangent lines. And that's good, because that's what a stationary point is supposed to do. That's supposed to be the location where the slope of your curve is 0. or in this case, I guess the slope of the tangents is 0. It's the same thing. And you also can recognize as well that these points, like I said, they behave the same way as a vertex behaves in a quadratic polynomial as well. So we can also call these stationary points something fancier. We can call them turning points in this situation as well, because if you go up here with me, following the finger, once the function gets up to this stationary point, it actually turns around again. And then when it gets down to this stationary point, the slope of the curve is 0, but then it turns around and goes in the other direction. So stationary points can also be turning points as well. And we'll fuss with that, I guess, in more detail and more consistently later in this chapter.